Hey everybody, this is an overview of our nanoscience lab, which is to make silver nanoparticles using green chemistry methods. And as this is one of our earlier labs, I've included a lot of background information here in case you're not too familiar with chemistry. So first of all, what we're going to do is to make colloidal metallic nanoparticles out of silver, okay? Now, in case you've never heard of it, a colloid is defined as a system in which finely divided particles, which are about 1 to 1,000 millimicrons in size, are dispersed within a continuous medium, a liquid, in a manner that prevents them from being filtered easily or settled rapidly. And that's the definition from the dictionary. So it's also, to use this technique, it's a wet chemistry technique, that is one of the fastest ways to make metal nanoparticles, which makes it a nice gentle introduction to some of the fabrication methods for nanoscience. So what we're going to do is to mix an aqueous solution of a metal complex with a reducing agent. Now that might be a lot of words you're not familiar with. So first of all, a metal complex is a metal ion that's surrounded by other molecules or ions. The one that we're going to use for this particular lab is silver nitrate, or AgNO3. And you can also think of that as a silver salt. Now, a reducing agent is a chemical compound that chemically reduces others, so that's why they call it a reducing agent. But the way that it does that is by donating electrons. So when we're going to start with an aqueous solution of silver nitrate, and then you might dilute that aqueous solution with some more water. But we have AgNO3 dissolved in solution, and when that happens, when it dissolves in the water, it dissociates into a silver ion and a nitrate. So the silver has a charge of +1 and the nitrate has a charge of -1. And then what happens is the reducing agent donates electrons to the silver, and that causes the metal nanoparticles to form, the silver nanoparticles to form. Okay? And so over here on the right, you can see this is what silver nitrate looks like. Okay, now, once you start the formation of the metal nanoparticles, since they are so very small, they have a very high surface area to volume ratio. And a high surface area often causes a high chemical reactivity in materials. And so what that means is that once those nanoparticles begin to form, they are very chemically reactive, and so they have a tendency to get bigger and bigger and bigger. Well, we don't want that. We want them to stay nanoparticles if we're working on nanoscience. And so to prevent that agglomeration and to form a stable colloid, we often use a stabilizer, which is also oftentimes called a capping agent. Okay? Now, when the nanoparticles form, as they get bigger and bigger and bigger, if they get too big, what will happen is they'll precipitate out of the solution, and you might see some grit, what looks like grit or dirt, settle on the bottom of your beaker. Okay, so that's what to look out for, and that means that, you know, your nanoparticles are not nano anymore and they're too big. Okay, so the reducing agent that we're going to use today also has compounds in it that act as capping agents. We're going to be using green methods, and so our reducing and capping agent are going to be in the same solution. What we're going to be using are things like green tea, different kinds of tea, and also, just for fun, different beers. And I've provided you the papers from peer-reviewed journals that detail, if you're interested in reading them in their entirety, detail how this works, okay? There's been a lot of interest in recent years in using green methods to make nanoparticles. Silver nanoparticles are really interesting because of their antibacterial and antimicrobial properties, so people are excited about them. And the idea of being able to use green methods which don't generate a lot of hazardous waste and which are cheaper is a very exciting thing. So there's been a lot of recent papers about this. Now, stabilizers, let me explain about them. The stabilizers and capping agents that we'll be seeing in our labs this semester are usually surfactants. Surfactant means surface acting agents. And surfactants are oftentimes organic compounds, And oftentimes they have a hydrophobic, which means water-fearing, and hydrophilic, which means water-loving side, okay? And then what will happen is the surfactant will migrate to the nanoparticle, okay? And then the water-fearing side will stick to the nanoparticle, and then the water-loving side will face outward towards the solution. And in so doing, it forms a little coating on the outside of the nanoparticle, and then that coating sort of stops the chemical reaction that is causing the nanoparticles to get bigger in its tracks. So that's a very kind of happy, smiley explanation of how capping agents work. All right. Now, even though we're choosing one of the safest possible labs at all to get started on this, there are some safety concerns. As always, when you're doing any kind of chemistry, wet chemistry in a chem lab, you should wear long pants and closed-toed shoes. We're going to wear gloves, which I'll provide you, and some safety goggles to protect your eyes, which I'll provide you if you don't already wear glasses during the lab. And if you do have long hair, please bring something to pull or tie that back so that it can't get in the solution or get in your way. All right. We're not going to be working with any open flame. We're going to be using some hot plates to heat it up to the solution up to a max of, say, 80 degrees C. So there shouldn't be any real risk of this. But silver nitrate is flammable, so be sure to keep the silver nitrate solutions away from open flame. Also, you shouldn't really ingest or inhale the solution, despite the fact that we're using teas and beer to act as a reducing agent. Please don't drink the lab. That would be a really dumb thing to do. So don't ingest or inhale the silver nitrate solutions. It is a very low concentration, like I said, so it shouldn't be a problem. Also, though, don't get it on your skin, and if this happens, don't panic. Just, go over to the sink and rinse it with water. Okay? So it should be very safe, but please do obey the very basic safety rules that you should obey during any chemistry lab. All right, now what will happen is I'm going to provide you with explicit instructions on how to form these solutions, and that those instructions may differ depending on whether you're using the teas or the beers. So I'm going to provide you with those during the labs at the beginning of lab. But what you'll see, regardless, is you'll see the color of your solution change over time as the nanoparticles form. Now we're going to talk about why this happens in more depth later, but bear in mind right now that the color shift is super common for metal nanoparticles. And oftentimes, not for today's lab, but oftentimes some of these colors are very beautiful colors. And so these techniques for making these colloidal metal particles were actually cultivated as far back as the Middle Ages as a technique for making beautiful stained glass. So if you go to one of the old school cathedrals, right, in Europe, you might see gorgeous stained glass with different pretty colors, and that's actually oftentimes caused by metal nanoparticles, so that's neat. Now, different metals, different sizes of particles, different shapes of particles, all these things can affect what the color of the nanoparticle is. But in today's lab, using the silver nanoparticles in green chemistry techniques, you're going to see colors like the picture right here, which I borrowed from a paper from the International Journal of Drug Development and Research. So this was a paper on using green synthesis to make silver nanoparticles. And you can see the colors over there. It goes from like a light yellow to a dark yellow to a deeper brown. So that's what you're going to see, and you should see that shift happen to a deeper color over time as the nanoparticles form. Now you can quantify this shift in color and also use the quantification of the color shift to figure out what the size of the nanoparticles is. And we're going to talk more about that later, but I did want you to become familiar with the technique for how this is done. And so what people generally do is to take an absorption spectrum using a UV vis spectrometer. Okay, UV, of course, is ultraviolet, and vis stands for visible light. And so what we're going to be doing is looking at the absorption spectrum in the visible light range for these solutions compared to the control. All right? And then you get to get up close with a UV vis spectrometer. And we might also, if time allows, take the particles and look at them in an electron microscope later so that you can see what you made. Okay, here's a little schematic of a typical UV vis spectrometer that I took from a conference paper, reference given below. What most of them are, this is, well, what the one we're going to use today is called a dual beam UV vis spectrometer. And what it does is it compares the visible light absorption spectrum for a reference sample to the control sample and shows you, I'm sorry, from the reference or control sample to your nanoparticle solution sample, and that's shown here. So you have a light source that then passes through a diffraction grating or a prism or something like that that splits the light into its colors. And then you can guide a specific color of light to pass through a slit, which then hits a beam splitter. And then part of the beam will go through the reference sample and part of it will go through the nanoparticle sample. And then it hits photodetectors, and you can subtract those two spectra, the reference and the control, to see what wavelengths are being absorbed by your nanoparticle solution as compared to your reference. And that shows you how much the color shifts as the nanoparticles form. So that's basically how that all works. Now, for time reasons, and also because not all of the samples might give you the same, wonderful effects, we might not run all of the samples that you prepare, but you'll at least get to see them for some samples. Okay, so that's the plan. Now, for the UV vis, we are going to be borrowing the chemistry department's UV vis spectrometer, so be sure that you're nice and polite while you use someone else's equipment. It's on a different floor, and so what we'll have to do is perhaps decant the solutions that you've prepared into little cuvettes. You have to use these little square cross-section cuvettes for the UV vis spectrometer, and Dr. Puckett has graciously lended us those. So maybe at the end we should write her a little thank you note, but anyway. All right, so that's the plan, and thanks a lot for your attention, and I'll see you in lab.